Good morning, everyone, and welcome to the Trusted CI webinar for June 23rd, 2025. I'm your host, Jeanette Dopp-Heide. Trusted CI is the NSF Cybersecurity Center of Excellence, and these webinars are part of its mission to deliver high-quality, actionable guidance regarding cybersecurity to the NSF community. More information about Trusted CI can be found at trustedci.org. Today's topic is Towards Practical Confidential High-Performance Computing with Chenghong Wang. Dr. Wang is an assistant professor at the Luddy School of Informatics, Computing and Engineering at Indiana University in Bloomington. He is a core faculty member of the Security and Privacy in Informatics Computing and Engineering SPICE group and affiliated with the NSF Center for Distributed Confidential Computing. I have a few things to mention before we get started. First, this presentation is being recorded. Second, presenters are welcome to type in questions into the chat as the presentation progresses, and I will politely ask those questions as Dr. Wang is moving through the presentation, and we also will probably have time at the end for questions as well. And with that, I will hand things over to Dr. Wang. Dr. Wang, welcome.
Right. Thanks, Jeanette, for the introductions. And I'm also very happy to be invited to attending this webinar and to present my researcher's work. And I'm also very glad to hear that my research is actually pretty aligned with the missions for the TriCI. So just to get started. So today's I'm going to talk about the topics towards practical confidential high performance computing, which is actually my main task that my entire group is working on currently. So and I want to mention that this is also a work that is part of the NSF Center for Distributed Confidential Computing, and we actually merge lots of different directions in the context for confidential computing, and to achieve about the high performance version for the confidential computing is also a major mission and tasks that we carry on the CDCC. Right. So first, so I'll try to make statements like this. So we currently have a data shortage. Right. So, but apparently, when you see this kind of the statements, you might be pretty curious on why that is true, because we are talking about we are living in a big data era, and every day, so even a single company can generate terabytes of data every day. Why do we really have a data shortage at this moment? Okay, yeah. But I would like to see that this statement is likely to be true. And primary examples I want to show is about this. So a rare disease research. Okay, so rare disease research is an area that known to show off the high quality data, and only a very small, a tiny amount of data has actually been used by the researchers. So that, and as a result, it contributes to only a little fractions of the rare diseases can get actually approved treatments. So the reason is actually for rare disease cases, the known cases or data samples are actually across the world and distribute among different nations. And the problem is that there's actually a need for to internationalize the database, and we can just aggregate all of data together. But the problem is that due to the privacy constraints, it is apparently impossible under today's environments. The data points are distributed across different nations, and even different organizations and different countries will have their different privacy policies. And then it makes it extremely hard to aggregate or to centralize the data together. All right, so let's see some of the numbers over here. And up to the 2024, about 75% of global population is actually covered by privacy regulations. Okay, so that is actually a pretty large coverage, and we think that that is good because that protect our privacy. Okay, and also the more than about 160 privacy laws or regulations that is already enacted globally. But on the downside is that just because of this kind of strict regulations and policies, we actually found out that actually some of studies found that the medical research participants has been significantly reduced. Okay, so because we need to dealing with those kind of very difficult or very hard to comply policy or regulations, and people and researchers and organizations who has the data less willing to share their data with the others, and or even they do not want to contribute to some like the clinical trials or some of the other things. So that will have causes a significant drop for the medical research participants, and apparently it will slow down the research exploratory process for this kind of medical research. All right, so in summary, this kind of privacy policies may create some kind of dilemma. On the one side is that for medical researchers like the pharmacy companies, medical institutes, academias, they wanted to use real world data. Okay, so they want to carry out their research and to establish some new progress based on real world and high quality data. And on the other side, the organizations who have the data, like hospitals, they cannot share those kind of raw data to the researchers because of their facing strict privacy regulations. And actually, we are seeing that the data shortage gap is actually caused by this kind of the gap between the needs and the sources cannot share their data due to the privacy constraints. Okay, so if we have this gap, a very intuitive solution is that why not just trust like a centralized or big companies like Google and Amazon's like these third-party cloud service providers, or why not just trust some kind of HPC service providers like national labs, NSF funded centers? Can we just simply trust those and them to the auto source the computations to those kind of service providers? All right, so let me just go through about if we want to use this kind of flow, what would be the design looks like? Okay, so the data owners can now to so outsource their data. Okay, so they just outsource their raw data onto some like third-party cloud, Google clouds, Microsoft clouds, or we can also use some kind of cloud HPC providers by funded by the NSF. For instance, JetStream 2 is one of the kind of projects that is hosted by IU, which is also a cloud HPC, and everyone can also upload their data onto the HPC platform and to carry out some of the computations. Okay, so assume that the data owners upload their raw data to the cloud, and on the other side, the medical researcher can also do the analytical task. They post those tasks to the cloud, and the cloud process the request over the data and produce some results, and then return the results back to the nest. Okay, so apparently this looks pretty nice because first the cloud providers has large powers and they have large investments in the cybersecurity infrastructures, so they can have a better guarantees for the data security kind of things. And the second is the cloud and HPC providers, they have a large clusters, have huge computing powers, so that they can also carry out those computations very efficiently. All right. So everything looks nice, but this will still cause some problems. Sorry. Yeah. So there are actually some of the projects under this scheme. I want to just quickly mention. The first is Google has so back into the 2021, they have a project called Terra, and they just create some kind of data cleaning room, which is HIPAA compliant, and they use this kind of data cleaning room to host the NIH's medical data. The project is called All of Us, which host the thousands or 10,000s of the human genomes, real human genomes, into a data cleaning room. And the external academia researchers can also query this kind of cleaning rooms, but every single operations is subject to heavy human audits. So they just make sure that every operations is HIPAA compliant and there's no information leakage. So they claim to be that, but yeah, so I'll show that actually they may not eventually achieve that. Okay, another project is Accord, which is led by UVA, and that is also a HIPAA compliant remote HPC clusters that can use to analyze COVID data and medical data. Okay, So yeah, so everything looks nice, but we still have one problems and very critical problem is like this. So can we actually trust those large organizations? Are they actually trusted? So we still come back to some numbers, and we see that back to the 2024s, the healthcare records, when we consider the outsourced to the large companies like the healthcare providers and they use the cloud storage or some things, they are still suffering from a large number of a high volume of the data breach. Okay, so more than about 200 millions of health records has been impacted. And then actually, so they found that the health organizations' records has been more targeted, which means that they are more valuable for some of their malicious attackers, so they have higher risks. But actually, the big companies or the third parties, even the powerful, they invested huge monies into the cybersecurity infrastructures. They are still not doing a good work. So they still are facing lots of data breaches. And that also raises a concerns for the patients about like the 70% of patients are actually worried about whether their data and how its data is actually protected. So beyond, so this is even more beyond about the policy compliance. It is actually the current situations or the policy privacy situation guaranteed by those large companies are actually losing some kind of public trust. Okay. And on the other side, as I mentioned, so for every large companies, if they want to host this kind of cleaning room that is HIPAA compliant and can handle sensitive data, they will also spend a lot of money and spend lots of human efforts into those parts. And even they have done lots of work like this, they still are suffering from insider attacks. They have malicious employees or they have advanced hackers. So those can easily cause data breaches. And then the liability for those big companies are are pretty large. So you can see that for last year, a single fine against the Meta is just raised to 1.2 billion, which is also a very large fine or the cost for the big companies. So from both sides, the patients actually do not trust the large companies, and the big company or the third party provider is also suffering from the huge liabilities and make them unwilling to continue this kind of task. Okay, so and then so because we have this kind of difficulties and problems, and then so in a summary is that we see that the cloud providers actually have a lot of problems, and we cannot just simply assume they are trusted. Okay, and because of we have this kind of the problems and the cloud providers or these third-party providers may not be completely trusted, and then we are actually having some scenarios which is called confidential computing, and this is exactly targeting these scenarios and can help us to mitigate using some of advanced techniques to mitigate the trust criticized. Okay, so here I will just show some examples and give you a taste of how the confidential computing works. So it will be similar as the previous examples, how we use the cloud or third party to carry out all source computing. But the key point over here is that the data owners does not outsource the raw data. Instead, they only outsource the encrypted data and onto some untrusted cloud or untrusted platform or HPC centers. Okay, every data is encrypted and only authorized users and the data owners themselves can decrypt those. All right, and then so the medical researcher can also apply those requests and onto their third-party providers. This request can also be optional encrypted if they think about those analytical queries are also confidential or has intellectual properties. Okay, and something seems pretty magic is that on the cloud providers, they can just do computations over those encrypted data. So computation process everything that is similar to the that is over the encrypted data, and they can produce encrypted results. And the results is would be exactly same as if they has been processed the raw data. Okay, but remember that the third party, the cloud, still do not see anything about the raw data. They do not know what exactly they have been produced. What they can see is that everything is encrypted, but encrypted results is guaranteed to be correct. Okay, the results is sent back to the users, and the users can then decrypt those results to get the raw results for the analytical requests. Okay, so this is a kind of how the confidential computing works, and apparently, because all the processing pipeline has been encrypted, and then even if the cloud is untrusted, and then they still do not have any privacy or information leakages over here. So that is a general case or general example for how the confidential computing can achieved. Right. So yeah. And then, so the confidential computing will not, so generally have three type of guarantees. The first is very general, is provides the confidential guarantees. So all the data has been in transit to their clouds at rest, which means that have been stored, not used, or has been processed during the processing scenarios. Every stage will be encrypted, and no one, and including the cloud providers, they do not see anything in about the raw data. So that is a confidentiality guarantee. The integrity guarantee means that every data storage computations has been outsourced. They cannot be altered or tampered with without detections. So actually, confidential computing techniques will have advanced mechanisms to detect such kind of malicious altering or corruption. So if the data is broken, be modified without authorizations, that will be detected immediately. So to ensure about integrity guarantees. Okay, and the last one is called attestability. Attestability means that the entire cloud providers can also prove to the users such that they are carrying out the predefined protocols. So for instance, I'm asking the cloud to compute A plus B, and they must prove to me that they actually carry out the correct procedures to compute A plus B. And then they use the correct data, which is A and B. They are not compute A plus C or a multiply B. So that is a kind of things we can think about. That is, they can do the remote attestations, and they can verify to you they have run the correct protocol. All right. So and then so we now know about the general confidential computing guarantees, and then we are talking about what are those building blocks that we can achieve for those goals. So the first techniques that can achieve that goals is called homomorphic encryption, which is advanced encryption techniques such that the users can encrypt their data with some special key and then send to the cloud. The cloud can directly do the computations over the ciphertext. And when that ciphertext has been decrypted, that will be exactly the same as the cloud is carrying out the computation over plaintext. Okay, so it is a specialized encryption technique. The second technique is called multi-party computations, which is that we can involve multiple parties and to jointly and securely compute a function. So each party sends some inputs into the function, and the function will securely evaluate and reveal a result to everyone. So everyone only knows about their inputs and the results from the functions, but they do not know anything about the others' outputs. Okay. And the third one is called trusted execution environments, which is you can think about that is hardware isolation sandbox inside the today's advanced CPU chips or microprocessors. So they are hardware isolated. The resources are not shared. So every sensitive information can jump into that regions to do some advanced computations. So these enclaves guarantee that absolutely no software layers running on this host can interference, tamper with, or intercept any confidential compute information that is inside those enclaves. Okay, so if you're actually familiar with some industry terms about confidential computing, they are only referring to the last one, which is the trusted execution environments mechanisms. So they use they have bindings with confidential computing and TEs. They think they are the same, but when I'm talking about, I'm actually talking about three primitives, and these three primitives actually all of them can achieve the same goals. Okay. So for the first homomorphic encryption based techniques is unfortunately it is pretty it is both compute and memory intensive and can cause huge performance degradations. And most of the homomorphic encryption is dedicated to arithmetic operations, meaning that they are hard to compute, like the Boolean operations, like comparisons, evaluate the ReLU functions, something like that. And then, so the home of encryption is more like all sorts of computations. So every encryption must have a key. So I can outsource my records, but if I want to collab with the others, and then we will need some more advanced techniques over here. So this home of encryption is mathematically strong, but sometimes that is not yet practical in today's scenario. Okay, so multi-party computation is a little bit better one. So it is still suffering from a huge network overheads, but it can support both arithmetic and Boolean operations, which is most all the kind of computation they can support. And then, so you see that multi-party computations can be naturally fit for collaborative scenarios. So if I want to collaborate with some others without breaking our privacy constraints, that can be easily achieved other than home of encryption. Well, the third one is like the TE is just the hardware initiates the tools, and it is currently the best options for practical use because it is everything was enforced by the hard wires, and the only overheads is coming out from the secure IOs, which is way smaller than the other twos. Okay, so because of the advantages and the performance advantage for TEs, trust execution environments, so actually so our current research is more focused on this specific primitives. Although we also do some research on the other tools, but so consider about for our goals is to make the confidential computing more practical, and we are actually more focused on the TE techniques over here. Okay. And then, so even though we have the TEs, which is kind of hardware techniques, can help us to deliver confidential computing techniques, and we still have multiple gaps that we to achieve about confidential high performance computing. Okay, so the biggest issue is about performance. So the current TE scenarios, the confidential computing can still have pretty large overheads, and sometimes can achieve about more than 1,000 times. And then, so if we think about the HPC scenarios, it is apparently not practical because that is kind of the huge degradations, and that is apparently not high performance at all. Okay, so the second problem is about compliance. So confidential computing can guarantee that they have done they have set they have so initiated with trusted states. They have run the correct binaries, but they still can hard to provide the runtime compliance with some data processing policies. For instance, the confidential computing can prove to you that I have correctly run your request, which is A plus B and equal to C, and I reveal the results as a C. But whether this computation is policy compliant, whether it's HIPAA compliant, and whether it's compliant with some users' own policies for data usage, that is unknown. So, and that is not directly guaranteed by confidential computing, and needs some more works. And third one is about usability. Okay, so many of the current advanced confidential computing techniques, like encrypted databases, they do not have a good interfaces. Like you can just directly use Python to coding and to use SQL to do some of the query codings. They do not have those kind of features. Sometimes you will need to use lower level programmings to program those TE features or MPC features. So that is actually hard to be used by the domain scientists. So some scientists from the medical fields may do not even know about what is the TE and what exactly is homomorphic encryption or multi-party secure computations. So in that ways, if you ask them to program those kind of things, that will be hard for them to use. Okay, so and as a result, our group research is actually tackling those three kind of challenges. The first is we are searching for, working for the HPC native of confidential computing paradigms and the dedicated TE designs, and to deliver about the high performance of TEs and high performance of the confidential computing that is aligned with HPC contexts. Okay. The second is our direction is try to use a formal verification techniques and to help the confidential computing to formally verify their policy, privacy policy compliant. Okay. The last one is actually related to my NSF, the grant, which is we trying to make computational computing more usable for domain scientists, which is like medical scientists. We try to providing more abstractions for the users, and we also try to use some of the explainable privacy features so that the domain scientists can also understand. You do not they do not need to be the security expert. They can still use those kind of security features, but do not need those expertise. Okay, and then so for today's agendas, I want to try to pick one of the representative work in each of these categories and to introduce about our concrete progress. So I'm not sure if I can complete everything. So I will just try to focus on one part, and for the rest of two parts, I will just give you a highlights for what we are currently doing, so we can left some much more time for discussions. Okay. So I'll start with our first work, which is HPC native confidential computing and TEs. Okay. Which is actually our one of our most recent work that trying to develop a new type of TEs, new type of the accelerator TE. All right. So first, I want to show you some of the graph, which is a benchmark for the performance benchmark for current most advanced TEs. Okay, so you will see that the black box, which is native computations, which is we just directly run something on CPU, and then the other bar plots the computations under confidential computing or inside the TEs. Well, you can see that from this graph, you will see that the performance bottleneck is just around 5 times, which is kind of not exactly like what I mentioned can reach up to 1,000 times overheads, right? So this observation is correct because if we just simply duplicate the computations over here, just relocate an entire computation from a non-private into enclave, and then the overhead is not that large. Okay, so the actual problems for the overhead is actually coming from some other phases. Okay, so I'll just use some of the chain graphs to just get you understand why we have even larger performance issues over here. Okay, so first, when we're talking about confidential computing, all those projects currently they are focusing on the cloud settings. The cloud settings means that the design philosophy is still to do the resource sharing. Okay, so they use VMs, containers, and some other things, and to host as many tenants as possible. As a result, they use the CPU-centric TEs. So all those TEs you have been seeing so far, the mainstream TEs, SGS, TDX, they are actually all the CPU-based. Okay, so they build a hardware enclave, hardware isolated regions into the CPU microprocessors. And as a result, you will know that because of the CPU is managed about sharing stuff, they have rich microarchitectural leakages. The leakages means that even you have run the correct program inside the enclave, you will still leak some kind of side channel information like memory access patterns, volume patterns that can be directed from indirect channels, right? So and then, oh, sorry. So yeah. So I'll show a very good example over here and get you to understand why the CPU microarchitecture is coming from. So here you will see a very abstract figures for the CPU packager with 2 cores. Okay, and we know that the CPU is kind of microprocessors that is advocate sharing, resource sharing. So if we take a look at a single core, we can time share with different threads or processes. So those two different tasks can time sharing a same core, like using the round robin. Okay, so in that way, they will have some interference with some of internal states. For instance, they may have the branch target buffer, which is just to denote how the branch prediction works for your if-else the programs. So the program P0 may have altered the BTP, and then when they swap out and the P1 is a context switch in, and they may see some of the leftover states that is caused by P0. So this is some kind of internal interference, and this can cause us about side channel leakages. And the P1s, if that is malicious, they can just to infer some kind of memory access patterns or timing leakages that is directly tied with the P0's execution scripts. Okay, If we think about the two cores, even if they are on the two separate cores, like if we think about two programs that is running on two different cores, they are not interferenced by naturally, but they will still sharing some kind of features like L3 catch. Okay, and then if let's say that P3 is malicious, they can still create some contentions and to interference with P4. So in this way, the P4, if the P4 runs the sensitive data dependent operations, the P3 can still detect it from those kind of contentions. All right. And then, so this is what we call the shared microarchitectures that is inherent the problems with the CPU architectures, and which is what the main problems that makes CPU type of the TEs less secure. Okay. On the other side, CPU also have another problem is that they will use the open memory buses, which is the DRAM buses to connect it to the main memory. So it is well known that the DRAMs, the open buses can be easily snooped. So you can just probe very cheap probe over there, and you can just directly read the plaintext data in the memory bus. Okay, so combine those tools, we know that actually the CPU is not a good option because that can leak enough data over here. Okay, so and then so all this type of data, even you think about that is not directly related to the data, for instance, access and search patterns, but actually with those kind of patterns, we can actually launch a full database reconstruction, even if all the data has been encrypted. So that is pretty critical leakages actually. All right, so and then there are actually some of the mitigations over here. So that is some of the proposals is trying to do something like this. We are trying to isolate the entire core and we do not let them to do the time sharing. Okay, so a single core is running for a dedicated the programs, and we do not use context switching. And and another thing is we also partition L3 cache. The cache is also belong to the single core. Everything is partition. And the last thing is that the off-package memory is also removed from TCB, and then that means that all the computations must be within a single core. Okay, so over the green regions. Everything outside these regions will consider that is not secure at all or can subject to some of leakages. Well, so when we think about this design, it apparently worked because that has very strong isolations and mitigate about the sharing. But the problem is that the actual memory we can use is pretty tiny. That is only bounded to the L1, L2, and L3 caches, and L3 has even been partitioned. So that is very tiny space. What else? What if we want to use to run very large programs that is requires huge in-memory spaces? How we can do that? Okay, so and then then we can just come back to these figures, and if we want to make those kind of TEs to work over a large memory space and still to be leakage resistant and do not have those kind of leakages, and then we are coming to some kind of additional primitives that we call the data oblivious computations. So it means that every time when we use about memory, we need to use the branchless instructions. We have to make our programs to be constant times. And every time we will make sure that the memory access patterns, the request to the memory adjust the oblivious to the data. So every time it looks pretty random or independent from your data workloads. All right. So and then so this is and actually the actual reasons that can lead to up to 1,000 times overhead is because of the data oblivious computations. It's not attribute back to the secure I/O because secure I/O only gives you about 5 times overheads. And when you when you want to make the data oblivious, and then your overhead comes up with 1,000 times. Or in other words, if you really want to mitigate the microarchitectural leakages, and then you have to use advanced techniques additional to the original TE designs, and this will gives you about a significant overhead. All right. So I'll just give you a simple examples on what is Oblivious algorithms, which we call the Oblivious RAM models. And in that case, you will have better understanding on why the Oblivious algorithms can cause us a huge overheads. Okay, so on the left side, you will see that, which is a traditional RAM models. Every time when the CPU wants to access a memory, we just to do virtual to physical address translations, and we just directly fetch the catch line size of memory block into the CPU. So every time what we need, we just access the exact position for the memory, and that's it. Okay. Well, from the other side, what is ORAM access? So ORAM access is some kind of things. I want to access some of the memories in the memory pool, but I do not want the others know about where I am accessing, exactly position I'm accessing. So I will try to make more additional and random dummy records. And so my real access is hidden behind, concealed behind those dummy ones. Okay, and every time I will just read many more dummy records. On the other side, using the dummy only is not sufficient enough. Sometimes we will also need to do the shuffle. So every time the data locations in the memory will be shuffled every time when access happen. Okay, so in this way, we can guarantee that every single access is just looks completely same as random access. And in this kind of sense, we don't have any memory leakages. And this type of algorithm is called oblivious RAM models, and short for ORAM. Okay, and apparently every time you have reading more blocks, you have write processes, you have significant higher bandwidth overhead. Okay, so there's actually a lower bounds on any kind of ORAM algorithms, which is log 2 of m, every ORAMs or CPU-based ORAMs, and assumes a small or constant size of unobservable cache, we will have to suffer from this kind of lower bounds blown up overheads. But in practical designs, sometimes we may get even larger. We don't have a very good design for the optimal blown up. Sometimes we will have the log 2 squared and over end of the blown up, so which is even larger, and that is actually contribute to the man overheads. Okay, and then when we come back to this kind of the graphs, and then so we need to rethink about this problem into the HPC context if we want to do some of the confidential high performance computing. And then when we analyze this kind of figures, we see that actually the root causes for this entire chain, the entire overhead, is rooted back to the philosophy they are trying to design this confidential computing, because this is a cloud philosophy. And then so we're asking, when we think about the entire designs into the HPC context, do we still have this kind of overheads? And do we have some of the new phrases that can just mitigate this entire overhead? Okay, so we think about HPC philosophy is in sometimes we usually do not need CPU. We do not advocate for resource sharing because every workload is huge. We don't need to host multiple tenants, multiple workloads in a single accelerator. Sometimes we use a dedicated accelerator or multiple accelerators to host a single tenant's workloads. And we use mental accelerations. There's no software stake. And sometimes we will also use the CPU bypassing techniques because CPU is slow and we want to offload some of the workloads onto the dedicated accelerators so that the CPU is not always on the critical path. As a result, the design choices has also changed. We do not need CPU accelerators. In other words, we may need accelerator TEs. Okay, so accelerators like recently NVIDIA released the H100 confidential computing, and our own work, which is both or accelerator TEs. And then, so the critical question is that when we think about accelerator TEs, do we still face about rich microarchitectural leakages? Okay, so think about this. So this is a photo I have taken in the supercomputing 2024. And you will see that for the modern accelerators, we actually have a special type of memory which is called high bandwidth memory. Okay, so this type of memory is just directly located into the logical dice for the chip packager, so that their memory access channels is completely concealed. So even physical attackers are hard to probe into these memory regions. Right. And on the other side, as I mentioned, that those kind of accelerators is used for dedicated accelerations, meaning that we can actually make them to host a single tenant's data, and we do not need to make a sharing with the others. And recall that if we have a large memory that is unobservable, like HBM cannot be observable by the even physical attackers, and also we don't have the sharing that which is minimize the interference between malicious and honest users. And actually, we can think about today's accelerators can actually help us to create a very large unobservable regions that is resilient to side channel leakages. Okay, so actually, this has been already being proposed or being emphasized by many of the previous research, and people find out that when we use accelerators to build TEs, that will be super hard for attackers to steal informations or to exploit the side channel informations than traditional TEs like CPUs. And then, as posted by the white papers for NVIDIA's the Azure 100 computational computing techniques, the only thing about the possible attacks against the memory channels is only some hypothetical or physical attacks, like you use the electronic magnetic emissions, and use some others if they can do the chip depackaging, which is also we think about hypothetical. All right. So, and as a result, we can think about, if we think about move to the HPC context, it naturally have the accelerators that can create our observable regions for the large HBM. And we know that the high bandwidth memory is very large. So the memory regions is also pretty large for us, and we don't necessarily need some kind of data oblivious computations, because inside HBM, if the workloads can fit into the large HBM, for instance, in NVIDIA Azure 100, which is 80 gigabytes, we can just use data-dependent computations, because the attackers cannot observe those. And outside those, so outside HBM, we can still use data oblivious computations. But with those hybrid processes, we can actually reduce about overheads and approach to about high performance computational computing needs, because that can significantly reduce about our performance overheads. Okay, so this is our major designs is based on these key ideas, and I want to just quickly go through this. So the board is the engines that is built on the HBM accelerators, and which will have the similar TE features to isolate the executions. And the board will have internal HBMs and manages the executions all on HBMs. Every computation inside the isolated HBMs will be data dependent, so they can be pretty fast and use data dependent optimizations like hash tables, binary trees. We don't need anything about data oblivious algorithms. Okay. And on the outside, the host memory is still accessible by the board, the accelerators, but on the host memory, we will try to do the data oblivious computations over here, which is the same as previous work. Okay, yeah. So yeah, and another good thing, another important thing is that we want the board cores to be self-manage the processing logic to bypass CPU, because this will guarantee that the CPU will just be a relayer, and then there's very few informations can be revealed on the CPU from the CPU side channels. Okay, our prototype, we have built our prototypes on our workstations, and then so we just have that prototype built on the U55C FPGAs, and then so on the right side, which is a schematic diagram for our accelerators, you can see that the green area is actually our routing resource usages. And the usage is pretty efficient, because a large area space is actually unused. Okay, so the rest of the space can be used for other computations, like you can just incorporate AI cores and then call our models to manage about the memory. Okay, So we will see some of the prototype evaluations compared with industry grade about the oblivious computations. So you can see that from the raw latencies, you will see that our the accelerators is way faster than industry prototypes, even for the state-of-art programs. Okay, and then so we also use some of the baselines because the previous work is implemented on CPU. So we try to use normalize the slowdown as a new metrics. So we compute the CPU and FPGA baselines, which is the same non-private KVS code. And then so we compile them, and then we compute the slowdown over the CPU group and our groups. So you can see that if we consider about slowdowns, our slowdown, the overhead is only 2 times over the non-private versions. But if you think for the traditional ones, it can be pretty higher. Okay. And then so yeah, because of our this kind of visions, we actually create new types of accelerators that can achieve the same security levels as traditional oblivious computations, but our performance is significantly better. Okay, and we plan to in the future we plan to deploy our the board accelerators as a secure disaggregated memory design, which is that the board accelerators will self-manage a remote or CXL memory pools, so that we have computer unions can just issue the high-level memory request to our accelerators, and our accelerators will self-host and self-process any kind of secure memory access. And this is also kind of sorry for that. Yeah, yeah, and this is also aligned with the trends for disaggregated data centers, and then pretty aligned with the future HPC development paths. Okay, and based on this kind of architectural infrastructure designs, we plan to support the serializable transactions, scientific analytics, and HTAP systems on the top of our infrastructures, and those will be based on the application levels. Okay, so because I feel like I'm a little bit out of time, so I will just quickly mention about our second work, and I will just leave some time for us to discussion. So I'll just quickly go through about the rest of topics. So so here we also have some of others research is working on how we use the formal verifications to ensure that we are policy compliant. The computation is policy compliant. So as we say that for the TEs usually receive the programs from analysts and the data from data owners. And the TEs can actually generate measurements, tell you that the device is authenticated, TEs is trusted, and also the computation is running on correct program and data. Okay, but the problem is that we do not know does this processing comply with privacy regulations. For instance, is that if the programs is trying to filter PHI, so the program provided by analyst is trying to extract the zip code SSN, and then we do not know that, we cannot detect that. Okay, so this will be a HIPAA violations. So and then so this entire thing is actually not directly insured by the TE. So if this violation happens, we cannot tell, we cannot stop the entire processes. Okay, so what we plan to do is that when we do something like this, we need to generate a verifiable report. The report says that the computation is correct, and then we will also see that the programs and the data combinations is also compliant with policy rules that is governed by the loaded data. Okay, and the tools we are using is try to use the formal verifications and to verify the entire things. But that comes with 2 challenges. The first is how we formally capture the semantics behind the privacy policies. And the second is actually formal verification is highly expensive. And if your program is super complex, and then it is hard to deliver very good performance. And then so our observation is like twofold. The first is that data processing workloads are actually predominate into these scientific tasks, so that we do not need to focus on arbitrary workloads. We can just focus on those data frames or data processing workloads, and that can narrow down our scopes. And the second is the privacy policy is actually well suited to some of the formal verification techniques like information control flow. Okay, so by doing this, our idea is that if we have some raw programs, which is data processing workloads, like using the data frames, Python pandas, or SQL, we just directly abstract them into some relational algebra-based operation diagrams or the execution flow. So every time everything has been abstract into an operators, a sequence of execution operators. Okay, and every operators can actually be formalized and artistically executed in the T environment. And our job is that we do not need to formally verify the entire programs. In the code level, we just need to formally verify that the relational algebra workflow satisfies the certain policy rules. For instance, if HIPAA says that no PHI shall be released, and our form of verification is that the PHI columns do not flow to the end, which is for the join operators you will see on the very top, and then we must have some of aggregations after that. Okay, so in that way is that we don't have any PHI columns to be flow out of those. Okay, so by doing this, we can see that so we have built our prototype systems, and we have tested on many of the actual use cases, and our checking time and running time is actually acceptable. So our tools can help you to formally verify your policy compliance for your computations, and also to within a considerable or reasonable time costs. Okay, so yeah, so and our next step from this is we will try to do we'll also try to apply our things on non-structured data, and we also to extend to data proofness, not to simply verifications, and we also try to explore some verification accelerations over here. Okay. So the last one we want to talk is about the usable CC for domain scientists, and our idea is pretty similar. Is we want to try to fill those kind of gap between the scientific programming and CC programming, or also scientific maintenance and CC maintenance, because those have clear gaps. And our general idea is that we also do some abstractions. We want to integrate it with existing tools, and then so we use some kind of task levels abstractions for all those kind of programmings. And then every time is that, and we build some compilers, and those compilers will be compiled to like confidential computing microcode ISAs, and can be directly run onto different platforms. So the users will directly still apply to the interfaces at Databricks and Sparks, and on the lower levels, we will handle everything. Okay, for the maintenance, we want to build something like this. So we want to visualize your privacy risks, disclosure risk, and with your settings. You will see that for the figures on the right corners, lower right, we will give you some of the risk disclosure figures, and based on your current settings. So even though the administrators do not know about how to adjust those privacy features, they can still visualize from the visualized results. They will see that what is the actual disclosure risk under certain attacks. Okay. All right. So I think that's all what I want to introduce today. And sorry for a little bit over time. So actually, so a quick summary is that we have. So our team is trying to solve all the related contexts to advance the computational computing to the HPC context. We are working on the HPC native TEs, and we try to use a form of verification to achieve policy compliance. And we also try to improve the usability for CCs, and to let the domain scientists can use those. Okay, and then so yeah. And yeah, so as I mentioned, that is all. So all those work is also part of the NSF Center for CDCC. So if you are interested in our missions, you can also visit our website on CDCC. If you have any any questions, feel free to ask, and I'm happy to answer any kind of the questions.
Great. I'm going to take the screen back and let people type if they have questions. So 1 second. Okay, can you see my screen? Trusted CI webinar series. I have a couple of community updates. Can you see that, Cheng Hong? Community updates. Do you see a screen that says that?
No, I just see my
Okay.
screenshot. Yeah, sorry.
Okay. Sorry about that. I I think my my computer is not not keeping up with the times. Okay, I'll just go over a couple of community updates and then we've got a question here pending. So our next webinar is Monday, June 28th. Um, and the topic is tips, trust, identity, privacy, protection, safety, and security with speaker Florence Hudson. The Trusted CI NSF Cybersecurity Summit call for proposals is open. And let me throw that link in the chat real quick. Uh, 1 second. Um, if you are interested in presenting to the Trusted CI Summit or at this Trusted CI Summit,
Sorry.
please submit your call for proposal. We've got a number of forms listed there. We're taking all different kinds of talks, and we're closing that June 30th, so next Monday at the end of the day. Oh, and then if you have any questions, of course, about the webinar series, you can always email us at webinars@trustedci. So let's go back to our question here. Okay, we've got a question from David. Thank you for the clear and accessible explanation of confidential computing and your work. My question is more high level and philosophical in nature. I've seen many presentations on confidential computing, including work on homomorphic encryption, multi-party computation, and TEEs, and it often feels like a perpetual game of cat and mouse. While confidential computing is promoted as a way to secure sensitive computation, it also appears to introduce significant complexity, performance overhead, and new attack surfaces, often without delivering the bulletproof guarantees it promises. It's clear you're passionate about and an advocate for this technology, but I'd really appreciate your perspective on my concerns. Do you think we'll ever reach a point where we can achieve both meaningful performance and strong security guarantees, or are we destined to remain in this vicious cycle?
Okay, so I think that's just a pretty good questions. Actually, I want to clarify. So talk about 3 points. So the first point is that I don't think we can have a zero trust of everything is bulletproof, everything is a super secure. So if we want to achieve that kind of confidential computing, I would say that that cannot achieve in very near futures, and then we may have some trade-offs. And we may need to go for a reasonable privacy or reasonable security. So in some cases, you will see that some of the privacy, like we talk about, was the case. So every single cases we must prevent. That could be very, very hard to have. But if we have some trade-offs for specific workloads, for specific type work, so we have a higher level of the privacy guarantees. And if we want to have that goal, that is achievable in the near future, I believe. Okay. And about the second perspective is I think is also my research is driven by this, which is I want to see that many kind of the TE techniques or confidential computing primitives, they have the assumptions. The assumptions is some kind of very that out of dated. Like some of the assumptions is back to the semiconductors in 1978, and they do not trust about the hardware itself can give you the hardware itself can give you very good about performance. So they will rely on some kind of cryptographic techniques and to make some kind of make this problem too theoretical. So they have theoretical merits, but from the perspective view of practice may not be very good. So if we look back into the today's semiconductor capabilities, we will see that we have many new hardware techniques, like high bandwidth memories. They already have a pretty good security issues, and then we can somehow embrace those kind of new techniques and a large traditional like confidential computing overheads can be thrown away. Like we can just reduce a kind of those complexity and use a newer semiconductor techniques to deliver very good about the performance. So I think in the futures, I think if we rethink about the problems, find the root causes and embrace new hardwares and the trends for moving from CPU to accelerators, and also do some of the trade-offs, for instance, dedicated to specific workflows, dedicated to specific policies, we will, I believe we can eventually get into a very good confidential computing scenarios. But if we think about everything into very theoretical parts, we want to have everything have lower bounds guarantees, have extremely secure, like cryptographic secure zero trust. And then I would say that that will be a 5 to 10 years research there.
Oh, and they replied, thank you for your comments. Okay.
Nice.
We're a little bit over, so I think I'm going to wrap things up. If people want to email you, you've got your email address up here. I can also include it in the follow-up email with the link to the video. Thank you again, everyone, for joining us today. And with that, I will end the webinar, and you'll be kicked out of the room, but but I'll be sending around the link to this video probably later today. So with that, thanks everybody. Have a nice day.